Welcome back. I would like to talk about motion planning with Astar. And you can directly download Astar algorithm from this link to your computer and start using it. And this is thanks to this author, Yucelen, and their co-authors. Basically, he took his time to provide this open source code that is highly useful. I highly recommend, and I also personally thank the first author for this nice open source contribution. Okay, so what is Astar? Astar is a graph-based method to find the shortest path between 2 points or more. In contrast to Dijkstra's algorithm, which I'm gonna talk about it. It is related to Astar. Astar is a spatial, in my opinion, a better spatial case. Astar takes into account not only the path cost P in reaching to a target, but also the cost H from the current node to the target. So while there may be obstacles in the environment, right? So you are here, the target is here. You don't know where the target is, but you can, you know that it is located somewhere if there are not obstacles. And if I go like this, I can reach the target. And this is the basically, Dijkstra's algorithm doesn't assume that, it just finds the target using the path cost. So if you have an unknown environment or a partially known environment, you can use both Astar or Dijkstra's algorithm. But the assumption on Astar is, you know where your target might be. And these heuristics may not be super accurate, but you kind of have some knowledge. Environment is still unknown, but you kind of have some knowledge. If you are doing a random search with no clue where the target is, then you need to use Dijkstra's algorithm. Again, Astar is a spatial case. In this video, I will also try to explain a little bit Dijkstra's algorithm so that you can get a feeling of it. As compared to Dijkstra, Astar is faster because of using heuristics. And like Dijkstra's, Astar is complete in the sense that it will find the target if there is a path to the target. So let's dive directly to an example. All right. So currently, this is my map, okay, 4x4. My starting position is at B. My target is located at N. And we have an obstacle in the environment. If I would like to go from basically a vertical or horizontal move, it will cost 1. If I make a diagonal move, it will cost 1.4. Why? Because distance from here to here, right? 1. So this will be the square root of 2. I just rounded for the sake of this video 1.4. And for this video, I will assume I know exact distance to the target, okay? So I know the target is located here. This is my heuristics, cost H. Again, cost P is basically my moving cost, 1 and 1.4 for diagonal. And H is my distance to target heuristics. Here you are the target, so distance is 0. This point is 1 unit away, 2 points away. This is basically, right, 2, this is 3, so you find this distance as 2 to the power of 2, 3 to the power of 2 square root. It is approximately 3.6, that's why this is, 4.2. And this is 3 by 4, sorry, let's do it this way, 4 and 3, so right, 3 to the power of 3, 4 to the power of 4, take the square root, this line becomes 5. So these are basically rounded numbers that maps these heuristics. All right, so this is a graph-based method, so let me make this graph-based calculations. All right, initially I am at B, right? I didn't move, so my cost of moving is 0. Always inside this green circle that denotes my current position, inside this, I will always write the cost, which is coming from the path. And when I would like to determine the best move from one point to another, I am going to calculate the cost P plus H. It is not hard, guys. Okay, let's do it. So for example, if I would like to move total cost C is P plus H. In order to move this, I would like to move vertically. It will cost me 1. And for it is heuristics value is 5.6. So 1 plus 5.6 is 6.6. If I would like to move to A, my total cost is 6.6. If I would like to move E from here to E, basically it is a diagonal move. It will cost me 1.4. And heuristics value is 5. 1.4 plus 5, it will cost me 6.4. So for F, it will, I think you got the story, but let me calculate. Vertical move 1 plus, it is heuristics, so 5.2. And for C, you can calculate 5.5. Looking at these numbers, I would like to move to the smallest one because it is it will cost less. I am moving to F. All right, so I move my vehicle from B to F. I am right now at F. Inside here, I am writing 1 because I am writing only the actual cost that I spent, right? I moved vehicle from here to here, which is a vertical move, and it cost me basically 1. Now I am here. Let's calculate my cost in moving H. Moving H from F to H is a vertical move, 1.4, and it is heuristics of H is 4.5. So 1.4 plus 4.5 is basically 5.9. But I wrote 6.9 here because I am now also including my current cost. I am writing the total cost here. So 1 plus 1.4 plus 4.5, it is 6.9. You always calculate like this. What it will cost me to move I, right? Basically, from here to I, basically, it will be my current cost 1, plus it will be a move like this 1, and the cost, heuristic cost is 3.6. So total cost in this case, 3.6 plus 1, 4.6. Sorry, yeah, 1 plus 3.6 is 4.6. I am also including my current cost, which makes 6. You can also calculate all these others, but in this case, it is logical that this gives the lowest cost, so I would like to move to the I. Now, at this point, I realize something. I am going to drop A, C, E, right? Since the current cost, for example, moving to 8 will cost 8, but it is greater than the my previous cost, meaning that instead of going like this, if I go like this, it will cost me much less energy. So it doesn't make sense to keep this, since then right now moving to A become higher. So I am going to remove A. Same for C, greater than 5.5. Same for E, it became 7, it was 6.4. I don't need to update these numbers. I no longer need to keep these notes in my graph for motion planning. Their cost already become larger than the previous cost. So I am going to drop these notes from my graph. All right, so here we come. I drop this other notes from the graph. We are here. It cost us 1 and 2 to came to node I. I am calculating all these numbers, right? And as you see, let's calculate L and M. From here to L, right? Basically, moving to L from here is heuristic cost is 2, and it will be a move like this. 1, since I am going down, not diagonal. So 1 plus 2 is 3. I am adding 2, we are getting 5. I am writing the actual path cost here, and this is the total cost, including my initial cost. So M, on the other hand, I am here, this is a diagonal move, it will cost me 1.4. It is heuristics is 1, 1.4 plus 1 is 2.4. I am adding 2, 4.4, so I am moving here. In this case, I am dropping H, because if you compare h with the previous value, it was 6.9, it get higher, 7.5. So I can go to, I didn't go to h like this, and so I didn't go to h like this, and now I don't want to go like this from I to h, so I am dropping h from the graph, and basically I go to the lowest cost. Now my total cost becomes 1, 2, and diagonal move 1.4. My exact basic path cost is 3.4, and from here I am not going to repeat the same thing. The best decision, you have basically explore J, N, and L, your neighbors. From your neighbors, the lowest cost will be N, which is the 3.4 plus 1 plus 0, then you reach the target. So this is the shortest path. Starting from here, if you move like this, you get the shortest path. And to be complete, you can also drop L, since the current value of L is higher than the previous value, which was 5, and it get higher. I am also dropping them from the graph, so you reach the target. So to give you a feeling, this is the MATLAB I mentioned at the beginning of this video. I am using basically this one. Download it, it is very effective. Basically I run this, I put some obstacles to the environment, and I determined this to be my initial position, and it directly calculated you the shortest path. Great. This calculates using how I explained to you the Astar. So Astar is a pathfinder algorithm. Before I conclude this video, let me mention some stuff. Astar is a pathfinder algorithm that gives you the shortest path. For motion planning with Astar, you may require not only the path but also derivatives of the path, right? I mentioned in the previous video. In this case, if you need a smoother trajectory, and if the map is unknown, if you are implementing Astar in an online fashion, then you may want to use not this one but a linearized version of it. You may ask, what happens, if I need something, twice differentiable, then use a second order low pass filter. And so that this way you can obtain not only the path but also their derivatives, which sometimes you need for motion planning, not only the position or path but also their velocity and acceleration of the path. You can also use curve fitting to make it smoother. You can use, like the way I did in the previous video on motion planning with waypoints. This mostly applies to the after you explore the environment, if you would like to go back and forth, or basically select some waypoints. You don't need to select that much. For example, this, maybe in here to move away from this edge, here, like this, and fit basically a curve using non-parametric modeling, or you can use constraint function construction video. Then you use, you basically, if you would like to get so if you would like to make a smoother trajectory, select some waypoints as I explained to you, provided by the Astar, and then use the content from the previous video. All right, I hope you enjoyed, and let me know if you have any questions.